Today I'm going to talk about temporal interference stimulation for magnetic resonance imaging, which has varied applications from neurology to biophysics. Deep brain stimulation is a therapy being used to help treat pathologies such as Parkinson's disease, epilepsy, and many others. It also has applications as cognitive enhancement therapy. Temporally and spatially interfering electric fields, or TSI fields, are at the core of a new technique being worked on as an alternative to needle electrode deep brain stimulation. The old method of achieving deep brain stimulation is implanting a needle electrode deep inside someone's brain. This requires a highly skilled neurosurgeon to implant the electrode, a lengthy hospital stay, and a permanent electrode in the brain. Worse, it can cause severe damage to the brain. However, it is possible to stimulate deep regions of the brain by using TSI fields to create an interference pattern inside the brain, allowing us to stimulate these deep regions without stimulating the overlying areas. This effect is shown in Figure 1. You can see the electrodes placed around the head and the stimulation shown in red within the brain. To investigate this effect, we simulated TSI fields using CST Studio and Python post-processing. We created a computer model of a cylindrical saltwater phantom, placed 4 electrodes equidistant around the circumference of the cylinder, precisely at the center as measured along the height of the cylinder. We simulated electrodes placed around the cylindrical phantom as depicted in red in Figures 2 and 3. In the figure on the left, the electrodes along the vertical axis are paired, and the electrodes along the horizontal axis are paired. In the figure on the right, the electrodes on the upper left are paired, and the electrodes in the lower right are paired. These figures also show us the result of the simulations. A brighter pixel indicates a pixel with a stronger stimulation, conferring the TSI fields can stimulate deep areas. Future work involves confirming these results in the MRI machine using magnetic resonance impedance tomography, or MREIT. Once this is done, we can move towards examining these effects in humans, as depicted in Figure 4. This will be done by placing electrodes on the surface of the volunteer's skull, insulated with electrode gel, and then running alternating current through the electrodes while the volunteer is in the magnet. Sounds unpleasant. Ideally, by removing the necessity of restricting it only to the most desperate areas by making it a non-invasive treatment, this will then allow us to bring the treatment capabilities of deep brain stimulation to a much greater number of people.